Hello, and welcome to Lecture 24. Here in this lecture, we're going to cover the last section of Chapter 7, Section 7.5. And I'm sure having had this chapter already be a fairly heavy chapter with a lot of ideas and fairly complex problems in some of the sections, you would like the last section to not be that heavy. Well, unfortunately, you don't get your wish, because this section, in a single section, we're doing what could be done in an entire chapter. This is a very heavy content section here. We're going to cover a lot of ideas. Now, just keep that in mind. Be aware that maybe not all of this is going to make sense on the first pass. This is one where the different types of problems are going to be very important, because we're covering really a wide range of ideas that all have one commonality, which is gravitation. Okay? Now, the reason this is even in this chapter, which is really about rotational motion, or our first of two chapters about rotational motion, is because, well, orbits, whether it's the moon's orbit around Earth or Earth's orbit around the sun or satellite orbits, are circular, aren't they? It's a type of circular motion. So that's why we want to talk about it, but there's a lot of groundwork involved. There's a lot of laying the steps so we can get up to talking about the circular motion of satellites. We have to introduce something called universal gravitation. That's a big idea, okay? And in doing so, we also have to, because we want to use conservation of energy to solve some problems, we need to introduce the idea of universal potential energy, well, universal gravitational potential energy. So, there's just a lot of new ideas, but they do serve that purpose of order to be able to talk about satellites, okay? So, let's go, all right? So first of all, on the key terms, I decided to include this figure. It's from hyperphysics, and it shows that we're doing something different here. When we talk about gravity, universal gravity, we're acknowledging that gravity is one of the four fundamental forces, the fundamental forces. We've never mentioned the fundamental forces before. We mentioned Newton's laws. We've talked about lots of ideas of kinematics and conservation of energy and momentum. Certainly we've talked about a lot of physics, but we've really been missing a big thing. And that's that everything in the universe can be described by one of the four fundamental forces that we know of. There's nothing that in our known theories that excludes the existence of other forces that we just haven't discovered yet, but there are four fundamental forces, and they are the strong nuclear force, the electromagnetic force, the weak nuclear force, and the gravitational force. Now, in this class, or in the 2 semesters of this class, we'll also cover the electromagnetic force in some depth. We're talking about the gravitational force right now. The strong and weak nuclear forces are beyond the scope of the class entirely. But big picture-wise, this is pretty cool, because we can see gravity is in good company. It's one of this just fundamental ideas of the universe that explains everything, from the Big Bang to black holes to the motion of a dandelion blowing in the wind. Right? Gravity is there. It's driving everything. Okay. Now, what do we want to know about gravity? Well, in terms of big ideas, it has an infinite range. So anything that creates a gravitational force, that force becomes weaker and weaker at distance, but it never truly goes away, okay? Furthermore, it's very, very weak. The gravitational force compared to the other four forces is incredibly weak, right? So the strong force has a strength of 1, if we're kind of just balancing it out. By comparison, the gravitational force is 10 to the negative 39 times weaker. I mean, that's hard to even imagine how much weaker it is. Now, however, the gravitational force becomes incredibly dominant on the scale of planets and stars because so much mass has accumulated. So it's kind of the unique thing about gravity, okay? And then as far as this idea about the particles that transmit it, we actually don't know, right? We don't know if the graviton exists or not. Maybe you've heard about that in kind of popular science, right? So there's a lot of unanswered questions yet about gravity. But we know it's there. We just don't quite understand where it comes from, all right? But there is one thing we do understand, is it comes from mass attracting mass. And I'll mention that again. But first, let's establish something, okay? Now, if we're talking about this idea of gravity and where it comes from, and that's a different conversation than when we mentioned gravity before, by the way, because up to this point it's always been, there's gravitational acceleration, all right? And you multiply that mass, you got gravitational force. And gravitational acceleration is 9.8, no questions asked, right? But now we're going to ask the question, where does that 9.8 come from? Okay, that's the best way to frame this. Where does that 9.8 meters per second squared come from? And we'll answer it, okay? In doing so, we also want to establish a difference between gravitational potential energy, as we've seen it so far, and something new, which is called universal gravitational potential energy. Okay? And this is going to be kind of the key difference between what we're seeing now and what we've seen before. All right? But of course, remember, this is all to motivate talking about the circular motion of satellites. Right? It's just a circuitous path. All right. So Near the Earth's surface, gravitational potential energy, so PE with a subscript g, and I'll use lowercase g to talk about, specific Earth, surface Earth gravity, it's mgh, right? We're used to that. We've used that for, blocks sliding down ramps and loop-the-loops and, vertical springs, right? We've definitely seen a lot of mgh, okay? G is just a constant. It's 9.8 meters per second squared, okay? Yeah, it's a constant, but it's a constant specific to Earth, okay? And I've given you other gravitational accelerations. I've said, oh, let's do this on Mars. So you've already seen that obviously this isn't everywhere. Different planets have different numbers, but we just haven't ever shown where they come from, okay? So near the surface of other planets, it's also true that gravitational potential energy would be mgh with a constant g. Just, it wouldn't be 9.8, it'd be some other value, right? On the moon, it's about 1/6 of 9.8, whatever that is in decimal, okay? Okay, so, but here's the idea, okay? When moving great distances from the gravitational source, like the center of a planet or the center of a moon, g is non-constant, okay? It doesn't just stay the same, and is inversely proportional to the square of distance, okay? So that's a key idea, is gravitational force and the resulting acceleration by Newton's second law falls off with the square of distance, okay? That's universal gravitation, and that's universal gravitational potential energy, all right? Okay, let's look at the equations. No more ideas, let's get to what does this look like in equation form, okay? Well, obviously the equations have ideas in them, but you get my point, okay? So this right here, this is a great starting point. This is a new idea. This is the law of universal gravitation. This is actually Newton's fourth law, right? We've got, the three laws of motion. This is the law that explains where gravity comes from, okay? And what it is it's law of universal gravitation. It's mass of some object 1 multiplied by mass of some object 2 divided by the distance between the two masses, okay? And with some constant out in front. This constant is just an empirical fitting constant, okay? So here's the idea. We see gravitational force is proportional to the product of the masses, so the two things that are attracted to each other, and inversely proportional to the square of the distance between them. Any two things with mass are gravitationally attracted. There's a gravitational pull between every two things that have mass. You're gravitationally pulling by pulling on everything in your room. You're gravitationally pulling on the Earth. The Earth is gravitationally pulling on you. The moon is gravitationally pulling on the Earth. Likewise, the Earth on the moon. Right? You get the idea. Every mass attracts mass. Okay. Now the forces are so small for small masses that they're imperceptible, unmeasurable, but they become quite perceptible for large things like planets. Okay. But distance has a big effect. You get far away, that force is going to fall off pretty fast. Okay. This is what it looks like if I was to graph gravitational force and distance from the source. It falls off as a square of distance. All right, so that's it decays rather quickly. Okay? Furthermore, if we consider mass 1 to be the mass of the Earth, mass 2 to be the mass of the person, kind of think of yourself, r is the radius of the Earth, because that would be the distance from the gravitational source, in this case, the center of the Earth, or just the distance between you and the other mass. So really, when we say distance between two masses, we're talking about the distance between the center of two masses. Because it wouldn't make sense to say the surface, right? It's got to be the center. It's got to be the focal point of that gravitational pull. So if we, so in the case of the gravitational pull from Earth, it's the radius of the Earth, assuming you're standing on the surface, that is, okay? And then we would set Newton's second law. So we just set this force, because this is an external force, this would be the net force, and we'd set that equal to mass times acceleration, because that's always true, right? And this would be the radial direction, right? If we're thinking of our new rotational terms. So this would be net force equals ma, and if we solve for a, we would get 9.8. That's where it comes from. Using this, Newton's fourth law, known as the law of universal gravitation, combined with Newton's second law, F equals ma, you get 9.8, all right? And you get it because you just set F net, because that's what this is, equal to ma, and you cancel out the m's, okay? All right? Here's the g value, that constant. I called it a fitting constant. It's also called an empirical constant. Empirical means experimental. So this value has actually been determined through experiments. There's all kinds of sophisticated experiments that have determined it. Everything up through, gravitational waves and the most modern experiments to the twisting of quartz crystals, all these, and measured of laser diffraction, all these different ways we've refined and got our value. You're not always going to use all the digits here. I usually use 6.67 or 6.674 to represent the gravitational constant in terms of significant figures. Now, it's a very small value. It's times 10 to the negative 11. Its units, because it does have units, it's not like a dimensionless coefficient. Its units are force times area per mass squared. So Newton meter squared over kilogram squared. All right. And if we were to split this into base units, obviously we'd split the Newton into kilogram meters per second squared. And then you won't notice there's also seconds in there and so on. But generally, this is the way I always write its units: a mix of derived units and base units. Okay. That's also the most common way of seeing it. So real fast, the fact that it's experimentally determined, you might think that's weird. Why isn't it derived from something else? We don't know where it comes from. It is one of the 3 empirical constants of the universe. There's basically 3 tuning constants: the speed of light, something called Planck's constant, and something called the gravitational constant. And that just sets the universe. We don't know why. Maybe they were created due to the conditions of the Big Bang. Maybe it's because of multiple dimensions. We don't know. But for whatever reason, these 3 constants determine the universe. Are there more? Again, we don't know, but it appears that those 3 constants are it. Okay? Everything else is derived from them. All right? Pretty cool, right? So, that's the thing, right? We're talking about the fundamentals of physics here, okay? In order to talk about the circular motion of satellites. All right, so let's go on, okay? And then this is just the G that you plug into the Universal Law of Gravitation. Okay, so what's going on in this next line? So this is just Newton's second law, and this is just showing the derivation that I mentioned over here in the box, how you can find gravitational acceleration, right? Which we call little g for Earth. Excuse me. And here, since we're going to be talking about it in a general sense, like the gravitational acceleration on any world, right? I'll often in this section and kind of in this context, I will write it as A for acceleration with the subscript g to let you know that it's a gravitational acceleration, okay? And the cool thing is that when you do that, when you cancel out the little m, essentially the small body that's going to accelerate due to the world, the large body, then you see that we can define the gravitational acceleration as just the gravitational constant, g, times the mass of the planet you're on, or world, right, like a moon, divided by the radius of that planet. Now, here's the thing. What if you're, up in orbit? Well, in that case, r would be the radius of the planet plus your altitude, plus your distance from the surface. So this is just, r is just distance from the center. Or you can think of it as distance between the 2 masses. It's just that you cancel out one of the masses, so it's not showing up anymore in the expression. Right? But this is the way you can always find gravitational acceleration for anything. I could find the gravitational acceleration of Earth relative to the sun by plugging in g, the mass of the sun, and r being Earth's orbit around the sun. Right? So it works for any body, any free body. Okay? All right. So there we have Newton's second law related to this new idea, the universal law of gravitation. All right. So now let's carry on to some different related ideas, and that's potential energy. All right? So this is right here. Now, first of all, we're going to start with something we've seen before. A change in gravitational potential energy is equal to the negative of the work done by gravity. Okay? That applies to plain old gravity near Earth's surface, but it's also going to apply to this new universal form of gravity. And remember, the reason for that is because if gravity is doing positive work, then you're losing potential energy because you're moving down. If gravity is doing negative work, then you're gaining potential energy because you're going up. And it all had to do with the definition of work being force times distance times the cosine of the angle between the two. And if it's in cosine of 180 being -1, if this all sounds familiar, that's good. I hope it does. Otherwise, refer back to the lectures on work. So the first lecture we introduced work. Okay. So here's the thing that's going to be a little bit different. That's this is still true. This is always true. Okay. But here's the thing that's going to be different about this type of gravitational potential energy. Okay. We're going to define our change in potential as the gravitational potential at infinity minus the gravitational potential at some point that we're looking at. Okay? So why is that? Well, because we're always going to consider the gravitational potential energy at infinity as our final potential. And it's always going to be, some extra labels I forgot to mention, it's always going to be 0. Okay? This term right here. The gravitational potential energy at an infinite distance will always be 0. Okay? So this is because potential energy is 0 when r equals infinity. And this means gravitational potential energy is always negative. Okay? So you can change your gravitational potential energy. If you increase it, gravity does negative work. So that idea is held true. But as you increase your gravitational potential energy, you're just moving it from very negative to slightly less negative. Because the idea is that delta P, E, so the change in potential energy, delta PE, is PE final minus PE initial. Okay? Well, PE final is always going to be at infinity, and it's always 0. It's zero because there isn't any force there. Think about the form of gravitational force. It falls off with the square of distance. So as you move infinitely far away from your source of gravitational potential energy, like a world, the force approaches zero. So the potential energy should approach zero as well. Okay? So it makes sense to have it be zero at infinity. Now, by the way, potential energy, I mentioned this before, you can always define where your zero is. You could choose for universal gravity to put zero somewhere else, but it would be a mathematical pain in the butt. It's absolutely advantageous. It absolutely makes sense to define it as zero at infinity. Here's the thing. We also do it with electricity and magnetism. When people talk about atoms and electrons, they talk about the binding energy of the electrons to the atom in a chemistry class. And when an electron is ionized, it then has zero potential energy because it's sort of quote unquote escaped the atom. So I mean that's the same idea if you've seen that before. Okay, so it is still a little weird because it means that gravitational potential energy is always negative. Okay, so we'll get some more practice with this if it's not sinking in right away. And I have a good example that I think will kind of, shed some light on maybe the best way to think about it, to internalize it. So hold on to the idea now. Just take it as a rule, right? Gravitational potential energy is always negative because it's defined as zero at infinity, okay? Or else just goes to zero at infinity, okay? Okay. Another thing I want to show you is a graph. This is the graph of potential energy, its magnitude, as a function of distance. So the idea is that it's decreasing with 1 over r. And I can't show you the derivation because it requires calculus, but if you take this force and you do the appropriate mathematical steps, you can show that potential energy has this form right here, universal gravitational potential energy, okay? So it's kind of interesting. It's got an inverse relationship just like force. It's just that it has an inverse relationship to r instead of r squared. So again, it decreases with distance. The further you are from something, the less gravitational potential energy you have, because essentially you're moving so far away from it that you're starting to like not be pulled on it anymore. Okay? You're leaving the influence of that gravitational source. Now, right away, that's kind of different, isn't it? Because before, as you moved further and further away from whatever was your 0 point for gravitational potential energy, it got bigger, right? The traditional MGH part. As you went up and up and up, you got more and more potential energy because you could fall further and further. But here I'm saying that potential energy is going to be decreasing. Well, here's the thing. It's going to be approaching zero, but you still are going to be able to fall. You still are going to be able to turn all that gravitational potential energy into kinetic energy. And that's the key idea about it being always negative. Okay? All right? Yeah. So that's the crux of it, right? That's the rub. Okay? So here's the thing. When we take then not a change in gravitational potential energy, but just the actual value of gravitational potential energy, whatever is your current value of universal gravitational potential energy, it's actually equal to the work done. Because the work done by gravity. Because of the negatives. Check it out. If I just take this expression here and I say it's equal to this one, well, the negatives cancel. So your current value of gravitational potential energy is equal to the work done by gravity. Because gravity puts you here. Gravity pulled you down to your current location. I'll just go ahead and say it now, but I'll say it again in a few minutes. The whole idea of gravitational potential energy is that you are in a gravitational well when you're on a planet. Okay? Because you're attached to that planet. You're being pulled to that planet by its huge gravitational pull. You're at the bottom of a deep gravitational well. If you want it to escape the planet, you have to have enough kinetic energy to get out of that gravitational potential energy well, right? And so you can expend a large amount of kinetic energy and then leave the gravitational potential energy well, all right? But that well, as an analogy, kind of hopefully makes you think about why it's negative. You have negative gravitational potential energy because you're at the bottom of a well, okay? All right. So then it's defined, gravitational potential energy is defined as negative, always negative. The gravitational constant times the mass of the world that you're on, okay, times your mass, or the object's mass, divided by the radius of the world, okay? Or just your distance from the center of it, okay? That's your gravitational potential energy. It's always negative because you're at the bottom of a well, all right? Now, if you went off into deep space and essentially escaped Earth's gravitational pull, or at least, never came back to Earth, because of course you can never escape it because it is infinitely far, right? But it can become negligibly small, then in that case you'd be out of the well. All right? So let's think about conservation of energy, because if we have potential energy, we can certainly conserve it in the context of mechanical energy, including kinetic energy, okay? So then the sum of kinetic energy and universal gravitational potential energy, notice the uppercase G, right? I always use that for the universal case, as opposed to the lowercase g for on the surface of a world, right, like Earth. Okay, so then as we say, okay, well then the sum of kinetic and universal gravitational potential is 1/2 mv squared for kinetic plus the gravitational potential, which is negative, okay? So in that it truly is negative, right? It has to show up as negative in the value, okay? So that means that, and that's just gravitational potential energy, okay? That means if you want to consider I point out here, I've said this a few times, but it's good to have it in writing. For large distances, this gravitational potential energy replaces mgy, okay? That's the idea, which only applies near Earth's surface, okay? Now, one good use of this conservation of energy equation is to apply it to escape velocity. So if I consider this kinetic energy be the velocity that's going to allow me to never return to Earth, then I would solve Ke plus Pe sub g equals 0 for velocity to find the minimum velocity to never return to Earth. And that all I would do then is just take this expression, solve for v, right, take it set equal to 0 just like that, solve for v, right, which includes taking the square root of both sides, and there we go. The escape velocity is 2gm over r. And r is usually the radius of the Earth, like if you think for like a rocket, like the Voyager rockets that were shot with enough velocity to never come back to Earth. And it could also be some r larger than the radius of Earth if you're launching something from orbit, or if you're just considering some phenomenon that starts not on the surface of Earth. Okay? So, and the reason we're setting it equal to 0, because essentially what we're saying is that this is the initial energy, and then this is the final energy, is we're saying the final energy is 0. Because the idea is we're giving the rocket just enough energy so that it will speed away from Earth, not get pulled back to Earth from the gravitational pull, all right? And it will use up all that kinetic energy to finally be some infinite distance away from Earth and never get pulled back, right? It's an ideal case, right? Because it's some perfect balance where it's just going to drift out to distance infinity, whatever that is, and then like come to rest, okay? Because it will have used up all its kinetic energy, okay? But it does mean it's escaped because it will never return, all right? But again, the force is infinite, so the gravitational force would still be there. It would just be too small to measure. Okay? Okay, all right. So let's get into the types of problems we're going to see. There's 4 types. Luckily, there's actually quite a few really simple plug-and-chug ones. So there's simple problems that involve Newton's law of universal gravitation, sometimes Newton's second law of motion in one dimension. Okay, those are the plug-and-chug ones. Then we have some fairly complex problems that involve using Newton's law of universal gravitation in 2 dimensions. These ones are all about vectors. They're just they could be any other vector type problem, maybe like relative velocity, or let's see, it's something with conservation of momentum, So they're that type of vector problem where you got to take components and then consider summing up the components and so on. So we've seen that before, but we're going to see it now in the context of gravity. Okay, I just have one example of that type. And then we have type 3, fairly complex problems that involve Newton's second law of motion and universal gravitation combined with centripetal acceleration to analyze the orbital motion of satellites. Okay, so this one's all about satellites. And this one we won't use energy in this one at all. Type 3 is just about using forces. So it's actually, you can do all the satellite business with energy as well. It's either approach is valid. The approach that the book focuses on and that I'm going to focus on is doing it all with forces. Okay? And then finally, type 3, complex problems, both conceptually, probably more conceptually than mathematically, that involve universal gravitational potential energy and sometimes conservation of mechanical energy. All right? And that's actually type 4. Okay? All right, so red, blue, purple, and green. All right, let's do the simple ones first. Historically speaking, Newton's law of universal gravitation allowed for the mass of the Earth to be calculated for the first time. Based on the calculations from the ancient scientist Arasthenes, the radius of the Earth was fairly accurately known back in the 1500s at 6,400 kilometers. We know now more accurately to be 6,371 kilometers. And a generation earlier, Galileo had measured the gravitational constant, that's a generation before Newton, to be 9.8 meters per second squared. So with that information, what mass did Newton calculate? Well, what he would have done is, so he'd use Newton's law of universal gravitation and Newton's second law of motion. We have that F net equals Fg equals ma, which then we could rewrite as F net just being the universal gravitational force equals ma. cancel out m2, that's just our free body, whatever it may be, and then, right, and then acknowledge that g equals 9.8, because I showed you this before, but that time I solved for g. I said, oh, you can find g, but to find g, you have to know the mass of the Earth. But you can find g through other experimentation, so that means that really, maybe the real utility of this is finding the mass of Earth, and that's what it was used for, right, some 500 years ago, all right? And so then me, or m1, is the mass of the Earth. So then you say, oh, then the mass of the Earth, if you just solve for it, is then g, all right, because a is g, times the radius of the Earth squared, okay? And by the way, the reason that scientists would have already known the radius of the Earth isn't because they got a long measuring tape around its circumference or something. It's because they use shadows at the vernal equinox to find it, okay? So it's kind of an interesting idea. And then we divide by the Universal Gravitational Constant. This was known just by measuring the velocity of the moon, okay? So g was known or estimated based on the velocity of the moon, all right? And so there it is, the first time Earth's mass was estimated. Notice I was just using one significant figure to kind of reflect the rough measurements of the time, but it was about 6 times 10 to the 24 kilograms, right? So we finally had an idea of how massive the Earth must be. That's kind of cool, right? Because you can't just go put it on a scale. All right? So, example 2. What is the gravitational force between an average-sized human and Earth? Okay? And note that the radius of the Earth we're going to use here is 6,371 kilometers. Okay? And we're going to use the mass of the Earth as 5.972 times 10 to the 24. All right, so these are accurate modern measurements of both those values. All right, so here we have just the Universal Law of Gravitation, and we just plug it in. Right? So just plug in the gravity constant, plug in the mass of a 75 kilogram person. All right, plug in the radius of Earth, the mass of Earth, the radius of Earth squared. Okay, and there we go, 736 newtons. So the 736 newtons is exactly what you get by just taking m and multiplying by 9.8. All right, see? 75 times 9.8, 736. Okay, but of course, we just found it a different way. All right, pretty cool, right? We found it the long way, but we found it the way that explains why we can do it the short way. Okay, so in comparison, how strong do you think the gravitational force between Earth and the Moon is? I mean, the Moon's really far away, so, is it a comparable force? No, it's actually much, much bigger. That's because the mass is so much bigger. So here, our two masses are going to be, instead of 75 kilograms, the mass of the Moon, right, which is only about 100 times less massive than Earth, okay, so it's huge. And then the distance is much greater, however, right? The distance is about 100 times greater, okay? And of course, we're squaring it, but still, we're going to get a giant force. We're going to get the gravitational force between the Earth and the Moon is 1.98 times 10 to the 20 newtons. So it's about 10 million trillion newtons, okay? That's how much force our planet pulls on the Moon, and also how much we get pulled back by the Moon, okay? From Newton's third law, right? For every force, there's an equal and opposite reaction force. So that's a good point, by the way. For every gravitational pull, there's always an equal opposite pull back, right? So every time that something pulls on something with gravitation, the other thing pulls back on it, okay? Every single time. Okay, so example 3. Compare the gravitational acceleration on Earth to Mars, to the dwarf planet Ceres, and to a hypothetical Earth where we've kept the mass the same, but we've made it denser, made the Earth denser, and thus reduced the radius by 20%. Okay, so let's go ahead and find them. I've given you the value for Mars before, but now we're going to show where it comes from. So we're just going to use this prefabricated version here, right? This one, of course, it just comes from the Universal Gravitation Law and Newton's second law. I showed you on the last page and mentioned it a couple times. All right, so we're just going to go plug in the numbers. Right, this is fun because this way you can find the gravitational acceleration on any world. You can say, oh, well, how heavy would I? Because once you have gravitational acceleration, you can multiply mass to get your weight. So you could ask yourself, well, how heavy would I be on, in the clouds of Jupiter, or how heavy would I be if I was standing on Titan, a moon of Saturn? How heavy would I be on one of these exoplanets that I hear about in the news? And so you can just look up the appropriate numbers. All you need is the mass of the planet and its radius, and you can find out how heavy you would be. All right. Well, how about on Mars, right? How heavy are people on Mars? Well, the gravitational acceleration there is 3.73 meters per second squared instead of 9.8. All right, so you'd be less than half your weight. Things would fall less than half as fast. All right, so it's still, you'd feel heavy, but you'd also, be noticeably lighter. And it's not as dramatic as the Moon, because the Moon is 1/6, right? That's where you can, hop around. So on Mars, you'd just be noticeably lighter. It's kind of neat. All right, what about Ceres? Now, I bring up Ceres because Ceres it's a proper dwarf planet. It's spherical, so it's not one of those potato-shaped asteroids. It's the only dwarf planet in the asteroid belt. Kind of interesting fact. It's kind of like Pluto. Okay, it's quite a bit smaller than our moon. You can see right away that it's about 100 times smaller than our moon if you look at its mass. All right, and its radius is quite small. So it's okay. So you're like, okay, well, maybe the gravity's not going to be that great, but it turns out it's actually really quite small. This is gravitational acceleration on series. That's some small gravity. All right, so it's 6 centimeters, 6.62 centimeters per second squared. All right, so that means like things will noticeably fall. It's not like it won't be like being weightless. Everything moves down, but everything would move down at this like hard to imagine slow pace. I would love to see an astronaut walk under that type of gravity. I can't even really visualize it. Okay, and then last one, our hypothetical Earth. All I've done here is kept the mass the same, but reduced the radius. So 20% reduction means 80% is big, and there we go. We would be heavier because on a denser Earth, we would just be, well, just that, heavier, because we're just getting pulled down more. All right, and worlds like this exist as far as like the Kepler project, which looks it's a space-based telescope, looks at planets around other stars. They find these other types of kind of Earth-like planets, and some of them are smaller and denser, and they'd have gravity like this, right? So you'd be really weighted down. Okay, so interesting stuff, I hope. Now this next one is a bit of a cheat because it almost involves some of the ideas of centripetal force that we're going to use with satellites, but it's not a satellite, so I decided to include it here. What percentage of your North Pole weight would you weigh at the equator? I love it when I have an example that's just fits in one line like this. Not many do, and so of course you'll need some constants here. You'll need the radius of the Earth. You'll need the period of the Earth in its rotation because you have to consider its motion, and you're going to need the mass of the Earth. Okay, but let's see what it looks like. So the idea, zoom out a tad here, is we're considering a person at the North Pole and we're considering a person standing at the equator, and those two people will not weigh the same. They won't weigh the same because They won't weigh the same because the person on the equator is going to experience a centripetal force and the person on the North Pole will not. They'll only experience a gravitational force. And so the best way to think about this, and I talked about this a lot in the last lecture, is think of centripetal force as using up whatever external force there is. In this case, there's this non-contact force, this fundamental force of gravity. On the North Pole, all that force is doing is trying to accelerate the person straight down. But for someone standing on the equator, some of that force is being used up to turn the person, to actually accelerate them in a circle. And so then there'll be less of it left to pull the person straight down. That means that the person at the equator will weigh less. Now the misnomer, the misconception, the wrong way to think about it is to say that the person on the equator is being thrown off due to the centrifugal force. We know that's wrong because the centrifugal force is not a real force. It's a fictitious force. Okay? It only appears to exist. So another way to think about why the person is lighter at the equator is because they have inertia. They want to move in a straight line. The Earth is turning underneath them, which means they're always kind of being lifted up because by their own inertia, because they want to continue off and the Earth is falling away underneath them. Okay? So people are lighter at the equator, right? I mean, everyone talks about it, right? You go down to the equator, you can like jump 20 feet in the air, right? Now, not quite. Okay? So let's see. Okay? So at the pole, how heavy are you at the pole? Well, at the pole, let's see, right? Let's think about our sum of forces, or our net force in the radial direction, the R direction, okay? Well, let's see. We got the gravitational force going down. We got the normal force going up. And here I'm defining positive as down. So that's why gravity gets the positive and normal force gets the negative. There's no acceleration at all because you're at rest of the North Pole, okay? All right. And so then we can just say that the normal force is just equal to the gravitational force, which we now know has its form based on the Universal Gravitational Law as gmm over r squared, okay? And so then we just hold on to that idea because since after all we're not given a value of m, right? Because I didn't say how heavy you are, and since we want to find a percentage, we're going to end up taking a ratio. So, point being, m's going to cancel, okay? So what about at the equator? Okay, so at the equator is a different story. We've got the gravitational force going down. We've got the normal force, but now instead of it being equal to 0, it's equal to mac because it's got to be because you're turning, okay? All right, so there we go. Centripetal acceleration takes the form of v squared over r. Okay, so then we solve for the normal force because the normal force is what a scale would read. All right, so it's gravity minus the centripetal force. Okay, and then we got to find v. Well, we can find v pretty easily because the Earth is undergoing uniform circular motion. It's a circumference over period. The circumference is going to be 2 pi times the radius, and then the period is going to be a day. It's going to be 24 hours. 24 times 60 seconds. Okay. All right, So our velocity at the equator, anyone standing at the equator, is moving relative to the center of the Earth at 463 meters per second. That's about 1.5 times the speed of sound. So people are moving fast. Of course, everything is moving that same speed, so you don't notice it, but that's how fast you are moving relative to the center of Earth when you stand at the equator. Whereas at the pole, you're at rest. Okay? So that's a big difference. So is it going to show up in the forces? Let's see. All right? So all I'm going to do is just take a ratio of the forces and multiply by 100, because that will give me the percentage of my North Pole weight at the equator. So the equator weight divided by the pole weight times 100. Okay? So I'll just plug in the expressions. The numerator is going to be this one here, and I've obviously replaced f sub g with its full form. I'm going to cancel out little m. Okay? All right? Big M doesn't cancel, so we'll need it in our calculation. All right? And so we're going to simplify this a little bit. That's all I've done here. Algebraically simplify it. Okay? You don't have to, but I figured it'd be easier to plug in my calculator that way. Then I plug in my constants: radius of the Earth, the velocity, basically the tangential velocity, the velocity of the person standing at the equator. Make sure to square it, right? That I solved for because of universal rotational motion, right? Mass of the Earth, and then of course gravitational constant. Okay, multiply by 100. What do I get? 99.66%. Oh, okay. Well, that's not that big, right? That's not a very big difference. So the percentage of your North Pole weight, so that means you weigh 99.66% as much. So people aren't that much lighter at the equator. But on the other hand, that is actually a measurable difference. That means the reduction in the weight is only 0.34%, but you could definitely, you wouldn't even need a very expensive scale to measure that difference. I mean, that is an absolutely easily measurable difference. Just not quite enough to notice. All right? Well, that's cool, right? I think it is. Okay, so let's move right on. So I got one other simple one, just more of a concept question. The International Space Station, ISS, is at an altitude of 435 kilometers. It varies, that's kind of its average altitude, above the surface of the Earth. That's called low Earth orbit. They keep it low so it's less expensive to get to. Is the apparent weightlessness of astronauts in this station explained by their distance from Earth's center and this formula, right? Are they so far from Earth that they've nearly escaped its gravitational pull? Is that why they're weightless? All right? Well, no, not at all. Not at all. No way. Okay? It is not due to low gravity, since gravitational acceleration at the altitude is still large. Right? In fact, if we solve for it, right, if we use this formula, we find out the gravitational acceleration at the altitude of 435 kilometers, right? Because now my r is radius of Earth plus the cruising altitude. Well, now it's 8.6 meters per second squared. I mean, yeah, that is significantly lower than 9.8 meters per second squared. It's a much bigger difference than the pole compared to the equator, that's for sure. But that's still pretty big, right? That's still a lot of gravitational acceleration. Okay? So in fact, it says here, if the astronaut was at rest at that altitude, right? If they'd gone up there somehow and then were at rest rather than moving quickly in the satellite, then they would just fall straight down. And they would fall straight down at that initial acceleration, and then their acceleration would grow as they got closer and closer to the surface of Earth. Okay? And they'd have a bit of a problem once they entered the atmosphere. Okay? Because they start burning up. But that's the idea, is that there's still a lot of gravity at that altitude. That's not why astronauts are weightless. Astronauts are weightless for the same reason that someone in a falling elevator would be weightless. They're in free fall. Satellites are free fall. More on that in just a minute. Okay? But in the meantime, let's do that vector problem I mentioned. So this is the idea about just sort of using gravitational force between objects as just a force, and setting up these kind of hypothetical situations where you have masses that are just kind of out there. This would be kind of impossible to set up, but if somehow you're in deep space where there is no other gravitational force around, you could position masses and then notice that they gradually accelerate towards each other. Okay, of course they would at very tiny rates, but they would, and that's this situation. Is you position four masses of different amounts of mass in a rectangle. All right, and I give you the values. It is a rectangle, so x is 1.5 meters, y is 1 meter. All right. And then and m is 1 kilogram, and then each one is bigger. Like this one's 2 kilograms, this one's 3 kilograms, that one's 4 kilograms. Okay? So the setup is just all about finding the net force, because there's going to be a force. We're interested in the force on m by the other three masses. All right? So there's going to be a force in the y direction. There's going to be, which is the force entirely from 4m. There's a force from the 3m, which is kind of at an angle. There's a force from 2. All right, which is directly on the x-axis. The angle of the force from mass 3 we can find by considering the sides of the triangle, the ratio of the sides of the triangle, 1 and 1 point, or rectangle, excuse me, 1 and 1.5, so it's 33.7 degrees. And then the net force is the sum of all of them. It's not drawn on the scale, actually, it should be a little bit longer, the net force. Okay? All right, so that's the idea. And then what we're asked for is we're asked for the gravitational force acting on the particles, write the vector in terms of x and y and components. Okay, so we're going to do that. I go ahead and put in I hat, j hat notation. And then finally, what is its magnitude? And then what is its angle? So that's going to be that angle phi, because I asked for its angle relative to the y-axis, the vertical axis. All right, so that's the net force because of m being pulled by the other three masses. All right, like I said, it's all about just vector components. So you have a vector equation, saying that the net force is the sum of the three attractive forces from the other three, because mass attracts mass. Okay, and so then we're just going to split it up into components. All right, then expand on those components in terms of the actual angle, because only one of them has angles. The other two are just long axes, which is nice. So it's only F3, we have to worry about angles. Okay, and then, all right, we'll then expand that out a bit more. Now we're actually going to use the Universal Law of Gravitation, because each of these forces is a gravitational force. So you can see, this is where I have to consider the fact that they're all different masses. So the 2m shows up, and the 4m shows up, and the 3m shows up, and the angle shows up. All right, and then I just plug everything in. And this point is just numerical, and I just simplified it. And I went ahead and factored out the g, and I'm just leaving it here for now. So this is 2.1, and the other one's 4.51, and they're both multiplied by g, which is 6.67 times 10 to the negative 11. So in other words, the forces themselves are going to be really small. All right, so let's go ahead and write an I hat, j hat notation, and we can see, indeed, the forces are tiny. So the force is 1.4 times 10 to the negative 10 newtons in the x direction, and 3.01 times 10 to the negative 10 in the y direction. Okay? All right, that's because little, single kilogram masses that are just like a meter apart don't experience that much force. I mean, you can think about how small the acceleration would be. They eventually would creep towards each other if there was no other forces around, but it would take a long time, like thousands of years. Okay? But they would, and they would move faster gradually as they did creep towards each other. All right, and then I also asked for the overall magnitude of the force. So here we're just going to use the Pythagorean theorem to find the net force, the hypotenuse. And it's 4.98 times g, which gives us 3.32 times 10 to the negative 10 newtons. Okay? All right, and then finally we can find the angle. This is the phi relative to the vertical axis. So it'll be opposite over adjacent. Opposite's the x component, adjacent's the y component, since we're measuring it towards the relative to the vertical axis. And it's 25 degrees, which makes sense that it's not going to be, say the reciprocal of, or the complement of 33.7, because it's getting pulled more up than any other direction, because the biggest mass is up here, the 4m. And also the 4m is closer than the 2m, because the 2m is 1.5 meters away and the 4m is only 1 meter away. So there's more force in the vertical direction than any other direction, hence the smaller angle. All right, so like I said, it's very much a kind of typical vector component type of problem, but it's involving universal gravitation law. All right. So now on to satellites. All right, so I think, let me just because we got the satellite page and then we got the energy page, and we'll wrap this up. I know there's a lot going on in this lecture. All right, so 2 examples about satellites using forces. Back to the ISS, right, kind of the reason I had that other question about it, so we kind of could already be thinking about the International Space Station, very cool thing. How fast is the International Space Station traveling around the Earth at the above specified altitude? And how long does it take the ISS to make a full revolution around Earth? And when I say the above specified altitude, it's referring to that previous example. All right, so all we're going to do is set up the net forces in the radial direction. So there's gravitational force pointing towards the center of Earth. That's the only force acting on the space station. That's it. There's just one force. And that's going to be equal to ma. Ma is m times the centripetal acceleration. This is the same set of forces that we would have done for the person standing at the equator, except there's no normal force here because there's nothing supporting the space station. It's in free fall. The space station is in free fall. The only reason it never hits the ground is it's a really fast projectile where its downward curve matches the curvature of Earth below it. So it just never hits. It just keeps falling forever. All right? So then we can just solve for v from this expression. All right? And then we're going to acknowledge that r is the radius of Earth plus the height 435 kilometers. Okay? So there we go. Plug in our numbers, big G, the mass of Earth, and our total value here. Okay? All right, and then notice that we're not squaring r when we solve for v. It's just r in the denominator of the square root. And there we go, 7,650 meters per second. And this is the type of values that you tend to see for satellites in low Earth orbit. They're always going to be on the order of 7,000 meters per second, about 7 kilometers per second. They're moving really fast because they have to in order to never hit the ground. Okay, all right. So that's the necessary velocity for those type of satellites. All right. And then I asked for how long does it take to make a full revolution? So, how often does the International Space Station go around Earth? Well, here we're just going to use this expression from uniform circular motion and solve for the period t. All right, and we already know v, so then it's just a matter of just plugging in everything. Make sure to plug in the radius of the Earth plus the height. Okay, and it's 93.2 minutes. So everyone, if you look it up about the space station, it's one of the first things you'll see. It takes about an hour and a half for it to go all the way around the Earth, and that's true. All right, so that's pretty darn fast, right? I mean, it's just that's so much faster than an airplane, right? I mean, but the whole thing is that satellites are outside of the atmosphere, which is why they can go so fast and not burn up. They don't experience any friction, no air resistance. Okay, so let's do it again for a different type of satellite. Here, I meant to ask for the height as well, so I kind of added it in. So what is the height and speed of an equatorial geosynchronous satellite, whatever that is, right? This is a satellite that is located above a fixed point above the Earth's equator. So there's the explanation, but maybe it's a little confusing. They really exist, and what they are is they're satellites that have the same period as Earth. So remember how the International Space Station had a period of 90 minutes? Well, if you go further enough up, because you have to go higher up, then your period gets larger and larger. And you can put a satellite far enough away from Earth that its period is 24 hours. And if you have a period that's 24 hours and you put it above the equator, it will stay above that fixed location, right? Because it will stay like in synchronized motion, hence the term geosynchronous, with the ground below it. They're actually incredibly important. Geosynchronous satellites are the backbone of the communication network of satellites because they're always at known locations, so they act as relays, okay? But let's see that they have to be much, much higher. They are not in low Earth orbit, okay? So let's find out how high they are, right? So here's the idea. This is kind of drawn to scale. They're going to be way up there, right? So this is Earth. They're many Earth, or quite a few Earth radii up. That's a big difference than just 435 kilometers, right? They're way up there, okay? So let's find out how high they are. All right, so we want the centripetal force to be entirely gravitational for a stable circular orbit, just like we did above for the International Space Station. So we just have our sum of forces, Fg equals Fc. So in other words, gravitational force equals centripetal force, all right? And so there is our gravitational force, our net force. It's going to be equal to ma. All right, there is our v squared over r, okay? All right, r here is the radius of Earth plus the height that we're going to solve for. All right, and to find v, we use the notion of that the period of the satellite equals the period of Earth, because that's what it means to be geosynchronous, okay? So what then must be the velocity of the satellite? Well, then we're going to have 2 pi times the radius plus the height divided by the period, the 24 hours, right, but converted to seconds. And I'm just going to go ahead and substitute this in, all right, because I don't know h yet, so instead I'm going to plug it in. Basically, this whole expression is just going to be used in order to eliminate v, so we only have one unknown, which is h. We'll get back to v in a second, okay? So then I'm just going to go ahead and simplify things a little bit, and then notice then when you solve for h, you get a cube root, okay? This is actually, if you've taken an astronomy class and you've seen Kepler's third law, there's a cube root there. That's the same reason, all right? And then I just simplified this in terms of the algebraic expression, and then we're ready to plug in our numbers, all right? And we get, we're still plugging them in, there we go, 3.59 times 10 to the 7 meters. So that's a lot of meters. How about kilometers? Well, that's a lot of kilometers too, because that would be basically 30,000 or 35,000 kilometers. In fact, it's about 5.6 Earth radii, because remember that the Earth's radius is 6,000 kilometers, so 35,000 kilometers is about 6 times bigger, right, or 5.5 times bigger. So that's an interesting idea. That's really high. I mean, these are some of the highest man-made satellites out there, right? Obviously, the moon is much further, but this is a really high up satellite, but it has that advantage of being at a known point relative to the Earth's surface. Okay, now let's find the velocity. I mean, by this point, just plug back in, because now that we know h, we can just easily plug back in, right? And this is r plus h, by the way. So it's this whole expression here. All right, okay, yeah, because this was h, all right, and this value right here is actually r plus h, which is what you have here. Okay, all right, and then we get 3,070 meters per second. So here's a couple things. First of all, that's much slower than the International Space Station. The reason is because gravitational force is much higher up there, so you don't need as much kinetic energy in order to not fall. In other words, the curvature isn't as dramatic. It's a much bigger circle, so the curvature is less dramatic, so you don't have to be going as fast in order to never hit, or to maintain that circle. So it makes sense that it's much slower, at less than half the speed. But also consider how much faster this is compared to the speed of the person relative to the center of Earth that's on the ground. Because remember, we solved for how fast someone's moving 463 meters per second. So the idea is the person standing, let's think of an equatorial location. Let's think of Quito in Ecuador, right? So you're in Quito, in Ecuador, and you're moving at 463 meters per second. There's a satellite directly overhead, remaining directly overhead, a geosynchronous satellite. It's moving at 3,070 meters per second, but you're both keeping up with each other. It stays directly overhead. How is that? Well, because you have a much tighter circle, so you don't have to move as fast. This is a much bigger circle, so it has to move faster to complete the whole circle in the same time that you complete your whole circle, right? But your periods are matched, all right? And the satellite is stable because we took into account the forces, all right? So really neat idea, really, really neat idea. Okay, so let's wrap it up for the last page here, all about gravitational potential energy. So first, let's go back to the idea of being at the bottom of a gravitational potential well, okay? You are in an incredibly life-giving, protected by Earth's magnetic field, breathing an atmosphere, wonderful place to be, Earth, right? The basket of life as we know it, okay? So here we are on Earth, but also we're trapped. We're trapped at the bottom of a well. We're trapped at the bottom of a well. It takes an unbelievably huge amount of energy to get out of. Let's look. So what is the gravitational potential energy of yourself sitting in your chair in this classroom or at home? Okay, I meant to change it to sitting at home on the surface of Earth. By the way, you have a mass of 72 kilograms. Okay, that's you, right? Not necessarily, but this is an arbitrary you. Okay, so let's plug it in. So let's just find your universal gravitational potential energy using the formula. And I know this looks a lot like the force formula, but don't get confused because notice the R is not squared anymore. This is the gravitational potential energy formula. Okay, plug in our constants: mass of the person, mass of Earth, radius of Earth, not squared. All right, and there we go. Oh my God. For negative 4.5 times 10 to the 9 joules. That's how much negative potential energy you have. Because again, you're at the bottom of a well. It would take 4.5 billion joules of energy to escape Earth. For you to escape Earth, it would take 4.5 billion joules. You're pretty much trapped. That's a lot of energy. Not to say, the sun produces way more energy than that. We can harvest that much of energy from splitting atoms, right? So that energy is out there. It's not like it's unavailable, but it is huge. It's a lot of energy to escape gravitational wells. Okay, let's do something similar. Consider the change in potential energy to summit Mount Everest at a height of 8,800 meters using gravitational potential energy, the one that we've used, MGH, and then using universal gravitational potential energy, the new form, okay? And what is the percent error between the two values? This is a cool idea, right? How accurate is it to just use MGH and assume that G is constant for a rather large change going from sea level to the highest point on Earth? Okay, so here are the constants that we're going to need: gravity, radius of Earth, mass of Earth. Okay, all right, so we're just going to use a percent difference, which is going to be, zoom in on this, this is going to be the potential energy the old way minus the potential energy the more accurate way divided by the potential energy the more accurate way times 100. That will give us our percent difference. Okay, so then I just plug things in. Well, the little m cancels out, so whatever is the person summiting or whatever is summiting Everest, it doesn't matter because the answer is going to be independent of that mass. And then here I've just expressed the change in gravitational potential energy. It's negative, and then this is just factoring out the denominator between the final state and the initial state. Okay, so this is just final minus initial. We could distribute the negative in, and if we did, then it would become initial minus final. But here I left it out because I think it's more intuitive. All right, and then everything. These negatives cancel out, and when you do all your values, you get a difference of 1.17%. Okay, so there is an inaccuracy. There's an inherent inaccuracy with assuming that G is constant. All right, it's not giant, but there is a 1% error that you would get. You'd be overestimating your gravitational potential energy. You'd be overestimating. All right, because in reality, you wouldn't have gained as much gravitational potential energy as you thought going up to 8,800 feet because G got weaker as you went up. Okay, all right. So then a good question, what minimum altitude gain would cause a 10% error, like a really big error you couldn't ignore? All right, so we're just going to set up the same expression, here m is already pre-canceled, and set it equal to 10, and instead solve for h. It's a bit of a algebraic hurdle, so I'm just going to skip over it and just give you the answer. Just say solve for h, okay? And when you do it, you get 564 kilometers. So much higher than 8.8 kilometers, and even higher than the International Space Station. Wow, even higher than, but that makes sense because remember 8.6 was the value at the International Space Station. So you have to go a little bit higher still, all right, to get the full 10% error. Okay, so, kind of puts it in perspective that you can actually use the kind of the classical form of gravitational potential energy for really most things. I mean, including planes and not get that too much error, right? But you could get 2 or 3% error. All right, last one. Okay, so this one's about conservation of energy using the universal gravitational potential energy. Consider a small comet in the Oort cloud. The Oort cloud is where a bunch of comets are at, by the way, but I won't go off on a tangent. At the edge of the solar system, 25,000 astronomical units away. Astronomical unit, by the way, is the average distance of Earth from the sun. So one astronomical unit is 149 million meters. Okay, 149 million meters. Okay, so this comet is approximately at rest, so its initial kinetic energy is going to be 0. We're given its mass, and the question is how much work will gravitational force exerted by the sun do on this comet by the time it crashes into the sun? So first of all, we're going to need some things. We're going to need, by the way, I've just expressed that in fractions of Earth's radius. We're going to need the radius of the sun because we need it to crash into the sun. So that's the radius of the sun. And then we also need the mass of the sun because that's going to be the pulling force. All right, so we're just going to write here that the work done by gravity is equal to the negative of the change, which is just the negative of U final minus U initial. Okay, and then U initial is going to be not 0 because it didn't start infinitely far away, but it's just going to be the negative because it's still inside the gravitational well of the sun, but it's kind of just on the edge of the well, right? It's not deep inside the well. And there's the mass of the comet, mass of the sun, gravitational constant, and that's the original radius, that huge value, 25,000 astronomical units, which ends up being 3.73 times 10 to the 15 meters. Meanwhile, the final gravitational potential energy is going to be really deep in the well because here RS is going to be the much smaller value of the radius of the sun, right? So it's going to be 7 orders of magnitude smaller, right? Here it's 10 to the 15, here it's 10 to the 8, right? So the comet has gone a long way, all right? It's gone, well, it's 7 orders of magnitude, it's gone 10 million meters, okay? As it fell towards the sun. Okay, so here we're just going to write the work done by gravity. Okay, it's going to be a negative value, it's going to be a positive value because we have a negative of a negative, which is what we would expect. All right, and I go ahead and simplify it here. And so what I've done is then when you distribute the negative, you have the final radius ends up being the leading term because I switched the order in order to have the second term be the negative term. All right, so this is a nice clean expression of it. And then if you plug in our numbers, there we have. The work done by the sun in order to pull that comet in is a positive value of 1.25 times 10 to the 18 joules. So a huge amount of energy, okay? All right. And so then by using conservation of energy, all of this work done by gravity is going to have to, well, become kinetic energy, right? Kinetic energy of the comet. So we're going to do the same thing. We're going to have the initial kinetic energy being 0 because we're treating the comet as starting at rest. Its initial gravitational potential energy still in the well, but on the edge of the well because of its large radius. Then its final gravitational potential energy, a very large negative value because it's deep inside the well. And then its final kinetic energy because it now has a less, so the idea is it's going to be, we were dividing by a very large negative number, now we have an increasingly large negative number, and so then we're going to have, it's going to give us a positive velocity. Okay, so there you go, I just cleaned it up, distributed the negative, and then we have a nice expression for finding final velocity in terms of universal gravitational potential energy. It's kind of similar to what, way we would have found final velocity using the old form of gravitational potential energy. It's just got this extra ratio business going on. All right, and when we plug in our numbers, we find that it's moving at 6.17 times 10 to the 5 meters per second, or 617,000 meters per second. So really fast because it picked up a huge amount of energy because the sun did a lot of work to pull it that far. Okay. All right, so that definitely, kind of shows what you can really do with these type of problems. I left you some more for practice of this type as well as a few other types. And I hope this rather long lecture with a lot of content, at the very least, has been interesting and informative. And let me know what you think about it. All right, well, thank you so much for watching.